I work in Bragança, which is in the northeastern corner of Portugal. I'm part of the staff of Instituto Politécnico de Bragança at the Agricultural School, and I'm also a member of the Mountain Research Center. I replied to this invitation, and I devised something that I was asked to talk about desertification indicators related to soil. My presentation is divided basically on, 3 points: the presentation itself, the concepts, the methods, and the applications. You will have these presentations, I guess, and some more material, and I divided it in 4 documents. So somewhere in a few moments I will have to change to the next one. My idea is to go then from concepts to methods and then for an example of application. And I'm very sorry because I organized this thinking about more a training school, and because I teach for long, as you see, I'm very much used to the word school. So this is quite scholarly. Unfortunately, I did not prepare exactly a conference type of presentation, so it is for sure boring. I'll try to keep you alive for a moment, and the idea is to address the thematics that are here presented. The first idea is that we are talking about soils, and then we are talking about properties and functions of soils. We are also talking about those properties and functions as affected by degradation under a desertification environment. And we are finalizing, I would say, with to bring all this together in the soil-based indicators that allow us assessments of, or that we use in assessments of desertification. The last slide just talks about what I intend you to get from this session. Just to provide you some tools to apply, to manipulate, I would say to operate with indicators, soil-based indicators to assess desertification susceptibility. So it is quite short, this presentation. I'll ask for help, please. And let's go to the second one, which deals with concepts. I felt the need of talking about concepts, and the main reason for that is because I was not aware of your background. May I ask you, who's the one, or who's the, which one of you is used to deal with concepts related to soils? So, more or less, so not very much. So for those that are used to, probably this is even more boring. For the others, I expect not to be so. And we are starting with soil degradation and desertification, going to soil-based indicators, and we've analyzed with a critical topic on those indicators. The first topic addresses soil degradation and desertification. As you might see, you have soil and soil degradation and desertification. So we have 3 concepts here. And what I would like to address is these successively these 3 concepts, which I would like to have a common language to share with you. First, when we talk about soil, we may talk about many things in the sense that we address many scales. We talk about soil when we talk about southern Alentejo, which we'll cross tomorrow, as well as we talk about Bragança, Quinta de Santa Apolónia, Campos de Santa Apolónia, where I work, soil profile, as well as when I take a sample somewhere, I don't tell you where, a sample of soils, of a soil, I'm also talking about soils, and if I see an image of a thin section, I'm talking about soil again. So across all these scales, we have soils, and we have the problem of crossing those scales and the problem of devising the right methodologies to address those scales. Just for materializing what I said, we have an aerial photo in which we can have an idea of the soils and their distribution, in the sense that, for instance, you have here terraces, you have here barren land with rock outcrops, certainly. This is a forest area, and we have also soil when we talk about the soil profile. This one is taken in Cape Verde, where you can find all the horizons identified, and still soil when we have a sample in the hand and we are trying to get the texture in the field, or even when we see fungi in a microscopic image. Whatever we address soil. And soil, as the most skilled ones know, is, I would say, a two-fraction, three-phase, four-component body. It is a natural body with these characteristics. Combines three phases, the three phases or the three states of the matter, in two fractions, and is divided in four components, which are the atmosphere and the water in the porous fraction, and the mineral matter and organic matter in the solid fraction. Well, this is very important to keep in mind, because we have a body that has very complex relationships, because there are phase transitions, because we don't have only mineral component, but the organic component, which interacts, besides acting by itself in soil processes, it interacts with the mineral matter and with the two other phases. Well, when we talk about soil, we also talk about its properties. And this is an example of one of the most obvious properties, soil color. But we have physical, chemical properties that you might list in a long array. Texture, meaning grain size, structure, those that relate to to chemistry, which are pH, cation exchange capacity, etc. All those properties are devised basically and quantified basically to characterize soil. And to get us an insight in ecosystem functioning, as we see with the last presentations, and we are dealing with the functions of soil. So this is not really what it matters for us. What it matters is the functioning of soil, which is quite complex to address, as you might understand, taking into account simply the soil properties. We must know more. We must know processes, basically, and how properties can help us understanding those processes. I give some examples here: water storage in the physical side of the thing, buffering, chemical buffering, which is a very important function of soils in the chemical side, and finally soil respiration, which is a very important function on the biological side. Well, this is soil. And then we talk about soil degradation. What is actually soil degradation? That's a point that I've been thinking about for long. And I guess that because of you, I was able to define what I think it is the shortest definition I got in all these years. So I went to this. It's a disturbance that negatively affects soil functions, potential performance. I never got so short. So I'm glad that someone asked me to come here and to think about this. This is, we talk about degradation when we disturb. It's meaningless to talk about degradation in something that has never been disturbed in the sense that disturbed by man or by a certain circumstance, natural circumstance that was, I would say, triggered or promoted by man. Secondly, we are not talking about a disturbance that positively affects soils. We do not talk about degradation when we have a fertilizer that helps plants grow, that has low impact in soils and subsurface waters, and help us better feed the world. So this is not the case. This is when we have a negative effect. So the disturbance itself is not the problem, but the negative effect on what? On a function. On a function or a set of functions, interrelated or not, but functions. And what do we affect? The performance. What performance? The only way to address it is to think about the potential performance that is affected. Okay? So if I do not say that a degraded soil can be more degraded and still talk about the degradation, if I don't have a reference of a potential performance. Okay? So the idea of a reference is very important here, just to drive us in this difficult pathway. Well, I think with this we cover almost everything we can find about soil degradation, and this is a striking example that you all would qualify as soil degradation. Erosion here in a field, a lean field along a hill slope, with plowing along the slope, gives rise to rills, a very important set of rills in Trás-os-Montes, northeast Portugal, hill slope. Well, but this is just an image. What I wanted to drive your attention is for our compulsive move to classification. That's why I talked to you about a kind of scholar way of presentation. Normally we know something from nature, and we want to say, well, I'll put this in that box, I'll put that in another box, and the other in the third box. It's what we try to do when classifying degradation. Keep in mind, it's degradation, whatever classification we use. Normally, we are very simple. We divide physical from chemical degradations, those affecting properties, functions of soil that are related simply with the physical side of the soil, I would say the physical properties, and those that are addressing chemical properties of soil or its constitution, its chemical components. We have some examples. These ones are readily perceived. Acidification, salinization might be a soil degradation process or natural processes. Okay, we are not talking about those natural processes when we are talking about these acidification and salinization. I guess we talk about compaction here and something like that. I cannot read. But we create a third category in soil degradation, which I would call shortly loss. When we have the previous two, we have a disturbance. So we talk about a physical or a chemical disturbance. But when we have a loss, meaning something that is no more there after degradation occurs, we are talking mainly about erosion. Erosion is something that removes soil from the surface, and so we have a loss with chemical components, with physically removed, so the physical part goes away also, and with effects either on chemical or on physical properties. But unfortunately, there is not only erosion acting as a loss and the soil degradation category. In fact, this erosion again is accelerated erosion. It's a degradation process. We are not talking about geological rates. We are not talking about natural rates. Those are part of the evolution of Earth. This is why we have alluvial plains, and this is why the oldest surfaces in the world are lower and the younger ones are higher. That's because erosion acts. This is not the case. This is accelerated erosion as a degradation process. But I was adding here two more losses that we may see as a degradation process. Normally, we do not address them in this kind of approach. I'm talking about removal and occultation. This is quite Portuguese, actually, but I'll try to explain what I mean. Removal and occultation, I'm talking mainly about urban or industrial areas in which the movement of soil corresponds to a removal or a cover. We hide soil. Where we are hiding soil. Okay? This is a degradation process in the sense, or degradation status, in the sense that we cannot use anymore the soil with the functions that originally it had. And furthermore, it is a loss. When we talk about occultation also, it may happen in a different way. For instance, when you have a dam built and you have a reservoir, the flooded area is no more a useful soil. It is not removed. It is hidden. okay? Occultation, I'm not sure if this is quite the correct word, but it works in Portuguese. Thank you for understanding. Soil degradation and desertification. Well, we are crossing, we are adding too much words. In the easiest way I devised to show you the idea of this crossing is putting together those elements there. The highest one regards soil degradation, the lowest one regards desertification. This is the intersection we want to talk about, okay? Because there is the soil degradation outside desertification processes and desertification risk areas. There is desertification with no relation with soil properties or the soil itself. So let's concentrate on the intersection belt that we can find here, which addresses soil-based indicators. Well, this is what we want to list, and I'll start with this I would say division. I'm not sure if the national focal point will correct me, but fortunately he will do so. The UN Convention defined a set of soil-based indicators, but there are some others within the UN Convention which are not addressed to soil in the UN Convention. And I'll talk about both. The list is here. It's soil depth, soil stoniness. I'll describe this in detail. I joined drainage and permeability, which are split in the UN Convention indicators. Aggregate stability, I'm not sure if it is the correct translation from the Portuguese version I have. And slope gradient. Well, let us have a talk about each one of these indicators. Soil depth. Well, sometimes in English you will hear also thickness, okay? Don't worry, it's the same thing. Soil depth is the first one to come out when we talk about desertification. And why? Because we have in mind a sort of a mass balance model when we think about this. What is the mass balance model? It's basically thinking about the soil as the balance between two processes. Soil formation from downwards upwards. Actually, it works the other way around, it works downwards, and erosion on the surface. So if you have more addings on the surface than underground, then you deepen soil. This is what happens in the lowlands where sediments come and accumulate. But in steep land, you will find the reverse, which means that what is weathered and comes up to be part of the soil, in fact, the soil is deepening, the weathering front is deepening, we see it, we explain it the other way around. When you have that adding from the downward, the bottom surface, we have a washout of particles on the upper surface, which contacts the atmosphere and is subject to erosion factors and processes. So, if we keep the removal from the surface roughly equal to the one of progressing the weathering front, we will keep soil depth steadily. If we are able to keep conditions in the surface to limit the removal, the soil will deepen. And this means that if this does not happen, and we see the soil with a shorter, a lower soil depth than it should have under the natural setting, then we say that something went wrong. Okay? The removal at the surface was too fast for the weathering upcoming of particles to be part of the soil. So soil depth is a very or crucial indicator. Of course, you cannot expect to have very deep soils in very steep land, wherever you go, under natural setting or under humanized degraded setting. So I again go to the reference potential functions of soil. Okay? We have to be aware that this mass balance model works but has to have a reference. You cannot expect a 3-meter deep soil in a 15% or 20% slope gradient. You go to the mountains, in very wild mountains wherever in the world, and you see shallow soils. That's it, under climatic vegetation conditions. This is the reference. But when you go to a steep land and see a soil that is shallow, too shallow to even accommodate the rooting of the sparse plants that may grow under those conditions, then you say to yourself, what a wonderful world. Okay? This is something that is crucial to address when you address soil-based indicators. What is these critical thresholds that are set here? Oh, I'm very sorry. This is very important to talk about. Soil depth, as you will see further on, is so crucial that it represents, to a certain extent, the degradation cycle at work in a status. Because if the degradation processes goes on in such a way that you get shallower and shallower soils, you will have less water storage, you will have less space for rooting, you will have less volume to be explored by plant roots in extracting nutrients. And you will have a less important soil smoothing of, or you may say buffering also, of the soil temperature oscillations. Okay? If you have less potential to have biomass using the soil, you have a less cover. And if you have less cover, you have more probability of a washing of the surface particles. So the soil will become shallower. This is the degradation cycle. And that is the measure at a certain moment of that cycle. And when you say that you're in the critical, on the critical moment, when you don't have space enough even for, I would say, some grasses to grow their rooting system. Normally, it is taken somewhere in the 25 centimeters. Okay? It's palm. Palm? English. Palm? No sé. Palm is another thing. Something like 25 centimeters depth. Soil stoniness is also a very important issue as an indicator of soil degradation and also as an indicator of soil-based indicator of desertification. Well, this is something like we talked about when we addressed the mass balance model we have in mind, but adding a very important point there, which is selectivity. When we think about the mass model, the mass balance model, we think that the soil is washed out simply. This is a layer that we wash out. And this is a layer that we bring to soil from watering. Well, this is not exactly reality. In reality, the erosion factors that act at the surface are not able to remove all particles equally. They are selective. So what you see in soil, in fact, is the result of the mass balance added with the effect of selectivity. And in that sense, you have a sort of, I would say, stoniness profile. You may imagine that if you have a hard rock, you have watering in contact with the atmosphere, you have a deepening of this watering front, and so what was rock and the rock block becomes particles, which are still in the side of rock fragments of coarse elements, which have more than 2 millimeters size. If you go deeper in watering, you will have finer and finer particles. So as that under certain lithological conditions, you have very fine material that is formed. You don't talk exactly about the pedogenetical action if you don't have clay formation. So when you talk about clay, we are talking of particles that are less than 2 micrometers. Okay? So very small. In that sense, if you remove those, I was talking about pedogenesis. When we talk about erosion at the surfaces, is about washing of those particles that are easy to wash, and those are the fine particles called fine earth below 2 millimeters size. This is the main issue. If you wash out the smaller particles, the finers, then you have a relative increase of the coarser ones. And this is again the evidence I'm talking to you as an indicator. If there is too much stoniness at the surface, it is because the finers went out. And if the finers went out, the erosion was too accelerated. And if erosion is too accelerated, we have a degradation process. And if it is under an arid environment, or you have a risk, an indicator of desertification. This is very important. This one crossed with the stoniness to talk about desertification. When we address critical thresholds, in this case, we normally talk of a scale like this. From 0 to 5% rock fragments in volume, you say that you have very low rock fragment stoniness. From 5 to 15, you say that you have a low. And then you would have an average, a moderate concentration from 15 to 30. And you start calling it high content when you are over 30% in volume, and very high when you are over 50% in volume. Okay? I would say that 30% are the critical threshold to be aware to soil stoniness as a desertification indicator. I'll go back a little, if I can. These two are the, I would say, the core indicators. We have more drainage and permeability, which is not exactly in the model I've been talking to you about. We have aggregate stability, and we have slope gradient. I joined them, they are actually two indicators in the UN Convention list, because they do not address the same thing, but the result is not so different in the most common situations we have. When we talk about permeability, we are talking about something that is soil-based property, and it is also, to some extent, a function in the sense that is not a state, does not define a state, but defines a flow. What is permeability is also called hydraulic conductivity, is the flow, the speed of the flow inside the soil. You should think that that speed is dependent on friction, as all flow is dependent on friction. The difference between surface flow and porous media flow, the soil is a porous medium, is that the friction is much higher. You don't have a contact surface between the body of water and the bed that is comparable to what you find in a stream, in a river. You have much more bed than the body of water. And this defines the friction area and defines what is the rate of flow under these circumstances. It's much lower. When you talk about the permeable soil, you're talking about something like higher than 25 millimeters per hour. This means 2.5 centimeters per hour. So if you look to a snail, probably it will go faster. Okay? It's a very low flow, a low speed flow. I talked about a high permeability soil, but if you think about a low or almost impermeable soil, you're talking about something like 0.12 millimeters per hour. So it is a low speed flow. And this is critical for drainage. Why? Because the soil is somewhere in the landscape, the soil reacts to the water flow with those speeds, and those speeds affect the intake of water from rainfall to the soil body. If the subsurface flow is so low, the intake cannot be higher, so some water will be in surplus at the surface. And this affects what would be the runoff and eventually the flooding. But this is not the same thing, because one thing is flooding and the other thing is runoff. And one thing is excess precipitation, so water surplus in the surface, and the other thing is overland flow. Why? Because not only the infiltration rate and so the permeability of soil affects the volume of water that goes now in a surface flow over the soil. This is the triggering factor, but this is not the only factor. You have topography that concentrates more or less water in certain areas. In that sense, drainage is a broader sense indicator, depending on permeability, but also depending on topography. You don't expect to have poor drainage in a steep slope, even though you have a very clay soil where the water flow inside, the water distribution occurs at very low rate. Well, this is the basic conditions, I would say, but if we have soil degradation, normally we have an extra point to think about. Soil develops structure, meaning what? The four components that we addressed in that circle are not split apart as they were represented. They are forming a body in which the smaller particles act as a cement, as a concrete that joins together the skeletal part of the mineral particles, meaning the coarser particles. And that skeletal interacts with organic matter and defines a porous media. So, if you have a structural degradation, especially on the soil surface due to land degradation, which might be physical as compaction, which might be physical as crusting on the surface, then you have a change. And that change is reflected on the porosity and the permeability of soil. So, when you have soil degradation, you have a structural degradation that lowers permeability, regardless the effect of topography. And this is very important for runoff generation and eventually for flooding. Now I should add something that is out of the field of the mainstream we were talking about up to now. When you have concentration of water in lowlands, you have flooding eventually, and you may have also soil degradation. So, soil degradation in the sense that in the broader sense that we are talking about, even if simply physical, does not address always to erosion. It might address to compaction, to structural degradation. And this happens on flatland also. This does not happen also or always on steep land. In that sense, one of the, I would say, the most critical factors for structural degradation is the degree of wetness of the soil. You cannot form good and strong aggregates without a wetting and drying cycle. If the soil keeps wet, it does not work for aggregation. It forms a mass, a mass, not a mess, that becomes a mess also. It forms a mass that may be very damaging for permeability. And as permeability lowers, you have more risk of flooding. What do we talk when we talk about thresholds? Well, if you think about steep land with more than 15%, it's unlikely to have bad drainage in the soil. If you have lowlands, you might have bad drainage, of course. If those lowlands are associated with low permeability soil, which is not uncommon because they are depositional areas where the smaller particles may accumulate, then you have the coupled problem of topography and permeability. And if you have on that the soil use that leads to structural degradation, then you have the exact formula to make it very bad. Okay? So this is an important indicator, but actually in my region, in most of Portugal, I would say the 70% of Portugal, it is not the real problem. Okay, it is on the area we will cross, of course, especially in the finer textured soils, but not, for instance, in the northern part of Portugal. This is an aggregate, and it comes on account of permeability and drainage. Well, this is quite simple to explain. If you see you have patches of different colors, more yellowish, more grayish. This is exactly what you see when you have a high water table soil in which you have poor drainage. The colors change, and they change to the grayish. It is called clay. This grayishing is part of the reduction of iron oxides that occur in the soil. And so this is a good indicator of bad drainage. Okay? Rarely, very rarely, it occurs on the surface. It occurs normally on the subsurface horizons. But then you have an indication. You have an indication of a high water table that probably leads to bad surface drainage. Aggregate stability. Well, this would be the direct translation of what is written in the UN Convention list. I would rather prefer something like structural degradation or structural instability. Why? Because actually I think that structure is it's the broader sense we can think about the organization of soil particles. Aggregation is one of the parts, the most important one, because it's the one that defines the limit between the neighbors and the neighborhood, which is very important to define the critical size of pores. But anyway, it's written like this, and I will respect that terminology. Structural degradation normally addresses to these topics: compaction, aggregate instability, and crusting. Compaction is actually a reduction of the volume of the soil. And in what regards soils, we must think that the volume of a soil is not the volume of its solids. It's the volume of its solids plus its pores. And there is no way, except by removal, to reduce the volume of solids. They are there. The only way to reduce the soil volume is reducing the pore fraction. So compaction actually affects directly the size of the pore fraction, meaning porosity. And where water flows is on pores. So if you reduce the pore volume, you reduce the probability of storing water, the possibility of storing water, and to allow water flow redistribution within the soil body. When we address to aggregate instability, you address to something that happens naturally on a bare surface under rainfall. If the water drops from rainfall hit the ground, they disrupt by impact the surface aggregates, and they become instable. Meaning that particles are splashed out, redistributed on the surface, and as water gets in the aggregate pores, increases sharply the air pressure inside the aggregate, because there is air where there is no water in pores. If the water enters, then the air is compressed, because sometimes it cannot get out easily. And in that sense, the increase of inner pressure in aggregates actually ends with a sort of an explosion of the aggregate, a disruption by excess pressure, air pressure. In that sense, instability occurs as we have something impacting the aggregates, either natural rainfall or the passage of a machine, stepping on, something that disrupts the aggregates. Some are more resistant than others, but in all soils, disruption occurs. Crusting occurs strictly on the surface, meaning what? Compaction affects the soil body to a certain depth. Normally, aggregate instability is critically a surface issue, and crusting is strictly a surface issue. If I go further in the topic of describing what happens when the water drop hits the soil surface, you can think about something of this kind. You have a rough surface with particles of any kind, any size, and you have a splash, a selective splash, because not all particles are equally splashed. So the finers are redistributed, and you have a concentration of either finers in the depressions or coarser particles in the higher elevation positions. These concentrations are layered with time. And to a certain extent, if you have a concentration of particles of the same size, you have a monotonous distribution of pore size. And that monotonous distribution of pore sizes means that you don't have large pores. If you don't have large pores, you have a bad permeability. And if you have a concentration of finers, the fine particles, you have even a problem, an added problem, because the pores between two fine particles are much smaller than the pores between two large particles. Okay? So crusting is something that it corresponds to a disruption of the structure of soil at the soil surface with an extra consequence besides affecting permeability. It smoothens the surface of the soil. Meaning what? The excess of rainfall that might accumulate at the surface during a rainfall event flows faster with less friction. Okay? Better transport of water and soil particles by erosion. Sorry. I talked of this in my last sentences. What are the critical thresholds? Here it is quite difficult to define what is a critical threshold in what concerns aggregate stability. But we have a scale. In soil profile descriptions, when you describe a soil horizon, you need to describe the aggregation. You need to say what aggregates you see, their form, their shape, rounded, granular, prismatic, platy, and actually the size of the aggregates, meaning if you have big ones or small ones, and finally you have to define or describe their strength or their weakness. How do you measure that? You don't really measure, you assess. You take an aggregate and you compress it, and if it loses, it's weak. And if it stays steady, it is strong. And we have a scale of 4 classes. No no aggregation, weak aggregation, moderate aggregation, and strong aggregation. Normally, there is a relation with the organic matter content and the shape of the aggregates or the clay content also. The shape of the aggregates is normally associated with the clay content. If you have a lot of clay, you have normally a prismatic shape. If you have a high content of organic matter, you tend to have round shapes, granular shapes. And under those two conditions, normally you have strong aggregates, meaning they resist to a physical action. I would say that strong aggregates are good, weak aggregates are bad. Well, as in everything, the ones that are in the middle sometimes go to the left, some other times go to the right, and we'll see that on the next elections. So, slope gradient. It is among the soil-based UN Convention indicators list, but actually it's more a land feature than a soil property. But it is important, as you saw, for instance, for drainage, and it is also important for the idea of a mass balance, even selective approach to the soil degradation process. It has effects, obviously, on runoff and erosion, because it is gravity action acting. You don't have erosion if you don't transport particles from somewhere upstream to somewhere downstream. So it's gravity. And what defines the vertical distance between upstream and downstream is slope gradient. So the higher the slope gradient, the higher the probability of having faster runoff and faster particle transport by that runoff, meaning erosion. But when we think about this, we are thinking about terrains, I would say land like this. We may change topography. The first image that I showed you had some terraces seen from the sky, but they were really terraces, meaning we can change topography. If we can change topography, we can change this effect of slope gradient. And this is why we change topography. We change topography, creating a terrace in which the original slope gradient is changed to a platform, lower slope, so less runoff formation or generation and development, and a higher, steeper riser in which you don't care about that because you think you control the, at that size, you control runoff and erosion. So under these circumstances, you don't have the slope gradient that was originally there, meaning that you have normally a soil conservation measure in action. And this means that when you see in the field those terraced areas, you, I would say, clearly discard from the assessment slope gradient. It's meaningless under this circumstance because it is controlled by that topography change. Critical thresholds, I would say that everything, the limit for agriculture, I would say the limit for mechanized agriculture would be somewhere between 12% and 15%. Normally it is not advisable to have mechanized agriculture more under steeper slopes. Well, if you go to Timor, East Timor or Cape Verde, you will see people plowing in 45% slopes, but it is hewing. It's not mechanized agriculture, it's different. Okay, we are talking about mechanized agriculture, which is much more damaging to the soil. And so I would say that if we think about something more than 15%, we are already under a situation that is not very advisable from the point of view of land use, thinking about desertification and land degradation. Of course, you can be more strict and cautious, and in that sense you can get down to 8%. But you can also think that in some cases, if you do so, you would have so short area of land use that you wouldn't do anything with agriculture. So here we have I would say an indicator in which we can move the threshold according to technology installed, intensity of the land use, and of course the wishes of the land use planners, which are very strong. Well, I dared to add some other indicators as they are here, and they address something that is in the UN Convention, but not on the soil-based indicators, but on the vegetation, or yes, the vegetation indicators. The vegetation indicators include drought resistance and erosion protection. And I would address soil water storage and soil erodibility under these two topics, which are on the vegetation side of the UN Convention list. I would add finally two other indicators that are, from my point of view, very useful. The last one, I think it's very operational. The other one, I'm not sure, but okay. And just a small address to, a short address to these, to this indicator. Soil water storage is, I would say, a composite function, at the same time an indicator, in the sense that it depends on several things that we talked about. It depends on the fine earth texture and organic matter, in the sense that it affects these two components, these two properties affect porosity and the pore size distribution. You have a clay soil, you have more finer pores. You have a sandy soil, you have larger pores. So this affects the porosity, the soil pore size distribution. Organic matter has an effect on water retention, rising water retention to more than the clay and the silt and the sand particles would allow. For instance, you may increase soil water storage by more than 20% increase. I'm not talking about the values themselves. If you have about 5% organic matter in a sandy soil, okay, which has a very low retention capacity. In that sense, the components, the properties of soil, the fine earth part, are important to define what is the ability of the soil to store water. But if you have a very thin soil, very shallow soil, you may have a very high capacity of retention, but you don't retain a high volume of water. On the contrary, if you have a 2-meter deep soil in an alluvial plain, you have lots of volume of pores that may be used by water to store that water to feed plants. As well, you must think that stoniness means the part of the soil that is not fine earth. So that is part of the soil that does not retain water, because this is not true, what I'm going to say. We take normally rock fragments as impermeable, so unable to retain water by themselves. This is not exactly true, but we can take that model as granted. And so, as you have the volume of soil more occupied by rock fragments, you have less volume of pores available to store water. And in that sense, you should add these two to those ones. And in the end, it is much more important for water storage to have a deep soil with low soil stoniness than to have a high clay content or organic matter content. Okay? If you have a shallow soil, you will never have good soil water storage. If you have a stony soil, you will never have a good storage, volume storage of water. The degradation cycle again is set here. What do I mean by this? In the desertification environments, dryland environments we are talking about, water is a crucial element, a crucial resource. If you don't have water stored in the soil, you don't have the possibility to feed biomass. And so you lower biomass. If you lower biomass, you leave the soil more prone to erosion processes, meaning that you go on shallowing the soil. And this means a reduction of the volume of the soil depth, which has consequences to soil water storage. You may think also of what we said in the beginning. Depth and stoniness are the two crucial issues as indicators for land degradation and desertification. And the degradation cycle goes on as you leave less opportunity to biomass to grow. And if the only way to reverse this is to increase biomass and to increase soil depth, and with that to have more fine earth, with that you have more water. The next is soil erodibility related to erosion protection, that is an indicator on the vegetation side in the UN list. Well, we talk about erodibility. It's a new word, I would say. Before the 50s or the 40s of the last century, it did not exist really. Erodibility is the susceptibility to erosion of a soil, but of a soil itself, not the environment of the soil, not the land. It addresses simply soil properties, not slope, not cover, not rainfall, not climate. It's intrinsic of the soil. And there are a set of properties that affect erodibility, starting with texture and organic matter. Again, more organic matter protects stability, the aggregates, and increases soil porosity and permeability, so it's better. It increases the capacity of the soil to resist to erosion. Texture is very, very important in the sense that there is a grain size class that is very sensitive to erosion processes, meaning silt. If you have a silty soil, you have for sure a very erodible soil. Why? Because silt is in between sand and clay, as sand properties in the physical point of view, very small, no colloidal properties as clay, so it cannot form aggregates. The aggregates that are formed are very weak, and the particles are very easily washed out. You should think about silt as the most important fraction of loess areas. Loess is a dust deposit from old alien erosion cycles. They are very deep somewhere in some places in the world. In the Yellow River, you have the largest of the world plateau of loess, which brings the color to the river, because the river erodes the banks, and the banks are loess, and the river is yellow. So a large part of the sediment load of that river is loess. If those particles are on the silt size, it's because they were easily transported by wind, and they are equally easily transported by water if water hits the ground. Okay? So silt in that textured point is the critical grain size. You have sand, you have larger particles. You have clay, you have the possibility of aggregation. Coming down, structure and permeability, we talked about this. They are critical for the susceptibility of soils, and we have stoniness also affecting erodibility, in the sense that stones protect the soil from being eroded. And the critical issues, the critical thresholds in this topic would be something like measured by something like the soil loss, the average soil loss per unit rainfall erosivity. Okay? You measure, you assess erodibility this way. The unit rainfall, or the unit erosivity factor that exports or leads to soil export, is normally the rainfall energy, kinetic energy, times the intensity. You may not use, you're not compelled to use this indicator, but you can use, for instance, the rainfall itself, millimeters. When we talk about erodibility, you are talking about the loss of soil per unit rainfall. Millimeters, megajoule per hectare per year, megajoule per hectare per year, times intensity, meaning millimeters per hour of rainfall. Well, this is to show you that the values that I'll give you are quite tricky. A 0.04 ton per hectare per year per erosivity of rainfall, which is quite tricky to explain, is the critical, I would say, critical value to qualify a soil as highly erodible. Higher than that, it's high erosion. Lower than that, it's moderate to low erosion or erodibility. Finally, I'll come to this organic matter content, and I would say that it is very, very important to consider it even as an indicator, or might be developed in the sense to become an indicator of desertification, in the sense that it addresses a key issue of the soil function. You should think that organic matter is actually the result and the actor of processes in soils. It's a result of the presence of biomass in soils, their decomposition, their life cycles, and decomposition rates. And as all this happens, it's also an actor on those processes as a component that has nutrients, is a stock of nutrients, is a stock of carbon, of course, of carbon, and it is also an important property that affects physical properties, physical condition of the soil, and chemical condition. For instance, all the buffering of soil in what regards reaction is mainly due to the organic matter. You would not have so steady pH on the soils if you would not have organic matter. It would oscillate much more, which is very important to the ecology of soil biota. Well, you have a set of effects here, and something that is written down for runoff and erosion. I won't come back to this. I already addressed all this, and I would like to address this. Organic matter is the key issue to break the degradation cycle. And this is very, very important in dry land, because in dry land, organic matter is not brilliant in terms of content. And it has very big difficulties to become brilliant. So, if you manage to have more organic matter in the soils in dry lands, which is a difficult task, you may try to break, or go on breaking the degradation cycle, limiting the losses, limiting the damage, and trying to rebuild the biomass comfort conditions that it finds elsewhere in the world. Critical thresholds for organic matter. Normally we say that a soil below 2% organic matter is a soil with low content of organic matter. Well, in dry land, sometimes you don't reach 1. You might reach 0.5. So it's a difficult task, and you easily find higher values in wetter areas. Water, precipitation, and temperature are key issues on that regulation, but being a difficult task does not mean that it is an impossible task. Okay? For instance, in Trás-os-Montes, we have under shrubland an average of 6% organic matter, even in dry land. So it is possible. It is possible. There is agriculture, conservation agriculture measures, conservation agriculture practices that may rise organic matter and help breaking the degradation cycle. Finally, I would like to address some more topics on stonings. And the idea is to combine what we said about soil degradation effects as affected by stoniness, and what we said about soil erodibility as affected by stoniness. As I'm talking for long, I'll ask this young lady to tell me what did you get from this?
What I understood, I don't know if I'm right, is that it has the opposite effect. You were talking about stoniness as something that is not so good in terms of degradation. It means that is a factor that you have to take into account when there is more stoniness, more soil degradation. And on the other hand, you were talking about soil erodibility, saying that stoniness would protect soil from erodibility.
So
yeah.
that's the point.
That's the point, yeah.
Yeah, she's very good. How come the same thing acts on different different sides of the barricade? Is it a spy coming from one side to the other? This is something that leaves us with a problem, with a dilemma. On one hand, it is the result of a degradation process, so it is a degradation indicator. But on the other hand, if you want to measure soil loss, erosion on those degraded soils, you should not expect much soil loss. Why? Because they are there protecting soil. So how do you address things? Because you would say someone like Lúcio do Rosário, my dear friend, well, in the steep slopes with high stoniness, imagine, I don't have erosion almost. How come can I say that is a degraded land? That's exactly the problem. I cannot say that it's a degraded land because of the soil loss rate. But I can say that it's a degraded land because the washout of the soil in previous cycles. I cannot say the land is not degraded because I cannot measure the process. Of course I cannot measure. There is no soil to be washed out. That's why I think soil stoniness is a very, very important topic as an indicator. And I will explain you what is my point of view in that sense. If you find under a certain setting, climate, land use, topography, parent material, a certain amount of surface rock fragments, stoniness, you should ask yourself, is this the natural, the potential rock fragments that could be there? And then you would say, if I guess that the rock fragment content at the surface is higher than that potential, I would say land is degrading because there is washout of the finers and concentration of the coarsers. If I find a lower rock fragment content at the surface than the potential, then it is good news because the soil is conserving the finers. Okay, that's a good reasoning. Do you agree? I guess so. The problem is how to define the reference. And the reference leads us to the weathering profile. Meaning what? For a certain sense, and I guess I replied to someone that addressed me in the break. When you have, I would say, if I put for you the curve, you start in 100% rock fragments at parent material, hard rock. Only rock, no fines, so it's 100% rocks. As you go up to the surface, you lower that volume, and it will become zero if all particles were passed from the coarser to the finer part of the soil particles. This rarely happens because after all you find normally something on the surface. Attention, I'm talking about a regular weathering profile. If you have accumulations, if you have a different sedimentary parent material, you don't apply this model, it's impossible. Okay? But if you have this model from hard rock to the surface, you lower rock fragment content. Then you think about this. If you have the stop point here, and if you lower because you washed out the surface layer, then you will find more rock fragments. And if you add to these the fact that that removal is selective, you find even more. And so you will have a profile that is like this. Okay? A decrease and an increase. And it is quite common that you find a surface with high rock fragment content, cover, and you grab on it, and you get down, and 10 centimeters below, or even 5, you don't find so much of rock fragments. Okay? That difference between the subsurface and the surface is a very useful indicator. Because the near surface but subsurface would give you an idea of the potential. The surface would give you an idea of the real one. Attention, this comes to an equilibrium between the balance between the two. In the sense that as you increase rock fragment cover, you decrease loss rates, and so the equilibrium point is higher and higher. What do I mean? In Trás-os-Montes, in northeast Portugal, you may have that equilibrium point at 8% rock fragments, so a low rock fragment content, but you can have in the drier and steeper areas that equilibrium at 45% rock fragment, meaning a high rock fragment content. Okay? So it's not surprising that in those dry lands, steep lands, you may find stony soils, even if there is no exact degradation process acting. The natural setting, or I would say not the natural, the past history of the spot would lead to that equilibrium content. Okay? This is for you to think about, because it's something that I care very much about also. Thank you for your attention on this issue. A final topic, a critical review, I would say, on what we said about concepts, the need for an adequate indicator relies on process identification, and this is critical. As I told you, the model does not apply. The model that I just described sorry, does not apply in any soil. It applies in soils that have that watering profile. If you go to sediments, to transported soil, if you go to somewhere where that model does not apply, it does not work. So the application of indicators is restricted to the setting in which they might be representative of the models that support them, actually. This is data spatial and temporal resolution is a critical issue, and I'll be quite rude in this comment. In what concerns soil-based indicators, I actually do not believe, in those that I mentioned to you, I actually do not believe in the expression early warning. Early warning, I do not know how to apply it in soil-based indicators. Okay? because there is a time resolution that is not fitting the early warning. Sorry. Okay? Spatial resolution is important for what the colleague also said here, and I guess in a reply. Well, we have to map, we have to distribute, and those indicators that I talked to you about are obviously spatially distributed, but some of them are very difficult to address in spatial terms. One of them is permeability. One of the highest coefficient of variation of data sets in soil parameters is hydraulic conductivity, is permeability. We may find, we take a core of, or 10 cores and have from very low to very high hydraulic conductivity. And so it's a quite difficult matter to deal with. That does not apply exactly to depth and stoniness. That does not apply exactly, that might apply to organic matter in the different approach. Does not apply exactly to soil water storage. It's more stable, I would say, especially. But there are ways to deal with it. And there is something that is advisable in these approaches, the combination. Meaning what? We never rely on a single indicator. We combine indicators because, well, this is a tricky issue because in some of them you have a sort of redundancy. When I talk about permeability, I'm talking also about aggregate stability. When I'm talking about stoniness and depth, there is a relation between both in some areas, which is clearly devised in some works, for instance in Trás-os-Montes, and you know quite well the work of Afonso Martins, in which you have a clear relationship between rock fragments and depth. Well, it's, you can devise the equation easily on one side and the other side. But in some cases, besides that redundancy, it helps to combine, to bring more information, to have a real, a better insight on the problem. Okay? Well, I finished this presentation.